In this video, we'll finally get to the definition of Julia sets, and we'll start our investigation on quadratic functions in complex numbers. Here we go. Okay. So what we want to study is look at quadratic functions that look like z squared plus c, where c is a complex number. And we'll see how the behavior of the iterates of this function depends on this constant c. But you might be thinking, well, why are you saying quadratic? Because there are other quadratic functions. There's a couple coefficients missing. So in the most general way you could write, this is what the complex quadratic function should look like: az squared plus bz plus d. And what it turns out is that we can use a trick to reduce this to one of f z squared plus c case. So let's see how this trick is going to work. And this is a trick that we will come back to later in the week. So I think it's good to pay attention. So what we're going to do is, if we have a polynomial that looks like this, we're going to choose c given by ad plus b over 2 minus b squared over 4. I know that looks absurd, but it's what it works out to be. And we're going to look at this transformation phi that looks like az plus b over 2. So phi is like a linear transformation, so it's only scaling and shifting that's happening here. So how are we going to use this to reduce to z squared plus c? So here's the trick. It turns out that you could get this general polynomial p by first applying phi, then doing z squared plus c, and then applying inverse of phi. So we're going to make the one step into this three-step process. Well, how are we going to do that? Well, we first check this is equivalent. So I claim that this step, applying the function p, is same thing as applying these three functions. So let's check that. I don't know if I have room, so let me start over here. So I'm going to do the phi inverse of f of phi of z. So phi of z is az plus b over 2. Okay. I'm going to plug that into the function f, which looks like z squared plus c. So that's what I'll do next. But remember, the c is this guy. So I'm going to square az plus b over 2. And then I'm going to add c, which is the same thing as ad plus b over 2 minus b squared over 4. Let's simplify that a little bit. So if I square this out, this is what I get. And I still have ad plus b over 2 minus b squared over 4. Notice that the b squared over 4, at least those two will cancel out. So simplify a little bit. We need to figure out what the inverse of phi looks like. So let's just compute that. So okay, if I'm going to compute the inverse, I subtract by b over 2 and then divide by a, then I'll get z. Okay, so that's the phi inverse function. So I take this expression, whatever I have here, subtract b over 2 and then divide by a. So I take this expression Okay, I'm going to subtract b over 2. Then the whole thing is going to be divided by a. So b over 2 cancels that term. And there's 3 terms left. All of them have a in it. So we can cancel out the a. And look, this is exactly what p is. So applying these 3 functions in that order is the same thing as applying p. Okay, how does this simplify the situation? It looks like we created more steps for ourselves, but it's actually kind of nice how this fits, because if you wanted to do iterates, so let's apply the function p twice. That's applying phi f and then inverse of phi twice. Okay. But look at the middle part. We are applying phi and phi inverse in the middle. So they cancel each other out. We can undo each other. And then what we're left with is phi inverse, applying f twice, and then phi. So this is what we get. And this is same thing for higher iterates as well. So every time we do an iterate of p, but do it the longer way, the in-between phi and phi inverse kind of cancels each other out. And then what we're left with is all the iterates of f. And then there's one phi and phi inverse at the beginning and the end. But basically, the only thing that changes is the iterates of f in the middle. If we study the iterates of f, like the one in the middle, then we pretty much get the same picture for looking at the iterates of p, because the only thing to get to the other one, we just have to apply this linear function. So the only thing it's doing is maybe stretch and then shift. That's the only thing that's changing. So actually, this is great because if we're looking at all of quadratic functions, we're looking at 3 different parameters. So we have to consider how the iterate changes as you scale the a factor, b factor, and the constant d factor. So, and each of these complex numbers is 2-dimensional, right? So there's really 6-dimensional parameters that you're playing around with. But if you can only study z squared plus c, now we only have one constant, c, which is still 2-dimensional because c is complex, but it's a lot less thing to worry about. And we can just see how this function behaves depending on c. Okay, so that's great. We are reducing the complexity of the problem. Okay, so let's define Julia set. So Julia set is named after Gaston Julia. So Julia is a last name. And I'll define what this means a little bit later. So the Julia set is the boundary of basin of attraction to infinity. So basin of attraction to infinity is basically the domain, part of the domain, the complex numbers. When you apply the iterate, it blows up to infinity. Okay. And we're looking at the boundary of numbers that approach to infinity. There's a very similar concept, Fatou set, after Pierre Fatou, which is the union of domains of attraction. So there's domains where sequence kind of converges to a particular number, and you take all of the domains like that, and that's the Fatou set. We're going to denote Julia set by this is supposed to be fancy script J. of the function f. And Fatu set is going to be fancy script f of this function f. Okay. So we're going to look at the simplest case here, just so we can apply the definition. Let's look at the case where the c is equal to 0. So we're just looking at the function z squared and iterates of z squared. So if we apply this function n times, we get z to the 2 to the nth power. Okay, so very large power of z. Okay, we kind of know how they behave. So if we just focus on the modulus, if the modulus is less than 1, they get closer and closer to 0 as n goes to infinity. If the modulus is greater than 1, then it blows up to infinity. Okay. If the modulus is exactly equal to 1, then it's on the unit circle. So those z's look like e to the I theta. And if you raise those to a large power, basically e to the power of 2 to the n theta I. So angle is rotating in this circle. Okay. So if you stay with modulus 1, it stays in modulus 1. Okay. Note that if you pick any point on the unit circle, then some points outside of the unit circle has modulus greater than 1, so they blow up to infinity. And some points sitting inside of the unit circle are going to go down to 0. So if you're on the unit circle, you are on the boundary of base integral attraction to infinity, right? Because some parts go off to infinity and some parts close by is not going to infinity. So that means that it's in the Julia set. So Julia set is all the points, well, it's the unit circle. That's the Julia set. It's on the boundary because everything outside of the unit circle blows up to infinity. The Fatu set, so there's two basins of domains of attraction. If the modulus is greater than 1, it blows up to infinity. So everything outside of unit circle is one domain of attraction. There's another domain of attraction in the inside. Everything inside of unit circle gets closer and closer towards 0. So that's another domain of attraction. So the unit of these domains of attraction is Fatu set. So everything inside and outside of the circle is the Fatu set. The circle itself is the Julia set. Okay. So more generally, let's make a notation for this. So if you have some f, we'll denote the base integral attraction to infinity by a of infinity. So this is any complex number where the iterates get bigger and bigger towards infinity. So the modulus gets larger and larger. And this I'm not going to prove. Here's a theorem. So the base of attraction to infinity is open, it's connected, and it's unbounded. And it is contained in the Fatu set of F just by definition, because Fatu set contains all this domain of attraction. And the Julia set of F coincides with the boundary of this guy, which is also the definition. But here's something that's good to know. It's always closed, and it's bounded, subset of the complex number. So it's Julia set is always closed and bounded. Okay. And this I don't know if this is clear from the definition, but it's something, the observation you can make is that because these Julia set and Fatou set is defined with what happens after iterating with f, applying the function f doesn't really change the set at all. So if you take a Julia set and you put that all the points in the set into the function, you're gonna get the same Julia set back. And same thing with the Fatou set as well. Okay. So that's what Julia set is. We're going to study more, a little bit harder example computing Julia set next time.